Okay, so first is the sectional property analysis and comparison that we have spent a little bit of time on that, and flexural response and bond response, and columns again with discrete fibers, slender columns. Now some work we are doing it on industrial flooring or your buildings with two-way slab systems. So a little bit that I'll say, okay. So moment curvature analysis that we talked about, maybe some of this thing may be repetition. Again, I told you why it is important is so that I can compare different cross sections, right? So what we do here is we assume strain gradient and we assume some neutral axis and then iterate it until the equilibrium conditions are satisfied, and then we go back and calculate your moment resistance, and curvature is the rotation of the section. So I know epsilon c, I know the neutral axis depth, so you divide it, you get your curvature, right? And this is more important, okay? This you pay attention. This is two different cross section with same amount of reinforcement at same location, right? What is that I get? I'm sorry, I couldn't put the cross-section dimension, but you got the point. See, steel is giving me 35 kilonewton meter. FRP reinforced section also is able to give me 40 kilonewton meter. That means ultimate strength point of view, both are giving me nearly the same, or even FRP is giving better strength. But what the problem is, you see, both of them are cracking at about 15 kilonewton meter because that's where the slope is changing, no? The light blue color and then orange color. Nearly they are changing the slope at 15 kilonewton. That's a cracking moment. But what happens after cracking? GFRP, you see, from 15 onwards, it has become really somewhat flat, and then it keeps going in a straight fashion. Now, what is the stiffness of this curve? Stiffness is the slope of this curve. So in the post-cracking regime, if you look at the slope, which one is having higher slope? It is a steel. M by P is nothing but, you have done your moment area theorem, right? In your structural analysis course. It is nothing but your EI, that is your flexural rigidity of your cross section. EI, that's it. That is what we said. If you put same cross section, same strength, same amount of rebar, the slope of GFRP section is going to be much lesser than that of steel. So this is, I can compare all these things. So ultimate strength point of view, absolutely there is no issue, but EI, the flexural rigidity, is much lesser for GFRP section. That means typically in a reinforced concrete member, what will be the level of service moment compared to ultimate? Can you take a guess?
Much lower than the steel.
Much, no. I mean, either it is steel or GFRP, I am taking
30%.
What would be the service level moment compared to ultimate? Let me give you a clue. What is the load factor that you use for your service calculations?
1.5.
1. No, service. 1. What is that you use it for ultimate? 1.5. So that means what would be the ratio of service to ultimate? 1 by 1.5, right? So it is going to be
65.
maximum that you are going to get is about 65%, right? So if my ultimate is 35, 65% will be roughly what, 25 or so, right? So at 25, if it is my service moment, what would be the curvature in this blue color curve? Roughly about 10. What would be that in this orange color one? That means the section is going to rotate almost 4 times that of what I am going to get. First T. That means more the curvature, more will be the crack width, more will be the deflections. So if I want to have, so I cannot allow the member to deflect as much as I want, no? Typically, what are the deflection limits that we have? That's what Professor Gangarao also talked about, right? What is the value that we'll have? There are 2 values that we check, right? Only for dead loads, permanent load, and then including long-term deflections after erection of partitions, you can never go more than L by 250. That is including long-term effects, right? Or 20 millimeter, whichever is less, right? So L by 250 is for buildings. For bridges, what is the deflection limit?
180. 600.
L by 800. short-term deflections. Why bridges we have? That's what I think Professor Gangarao talked about. I think I was there at that time. Why it is higher value? I mean, 800 is higher, but deflections are lower. Why we allowable deflections are lower in bridges?
Because there is load density is more.
Traffic volume is more, and then a lot of vibrations, and the passengers feel very uncomfortable, right? Because you're talking about long spans, right? We talked about that. You understand? So, for a GFRP then, if I want to limit the deflection, then what is it? I have to increase that EI. How would I increase EI? E is the section property. The only way is to increase that I. How do I increase I? I cracked, right? I put more reinforcement, then only the I will go up. Cracked moment of inertia. If I want to increase I cracked, I need to put lot of steel, lot of rebars. I should GFRP rebar. You see? So invariably, if I want to limit my crack width or deflection, I end up putting
More
GFRP rebar. Then what will happen to ultimate inflection? If I put more rebar, the section will become tension controlled or compression controlled? Compression controlled. You understand? So if serviceability is governing the design, invariably you will not have tension failure. Okay, that's the point what I'm trying to say. Okay, you got the point. Okay, now this is in serviceability regime. This is, if I zoom this thing and then look at it only up to 15, you see here there is a tremendous reduction in flexural stiffness after cracking. Up to cracking, you see blue and orange are all going, hugging each other and going. Right? The moment it cracks, the stiffness is lost for GFRP, and it picks up slowly because the elastic modulus of the rebar is less. That's what the problem. If somehow there are some manufacturers, if you can make GFRP rebar modulus to be even up to 100, then you are in the business. For that, then I need to use stiffer fiber, good quality resin, right? All those things are important. Resin will not play, fiber you should have higher stiffness, right? Right? So that then, you can really compete with steel, that's the key, okay? Okay, so moment curvature, I think this we have discussed about it, this I think we spent. Now you see, we have to test, right? So this is what I told you, the polyolefin fiber. So some of you asked, these are macro synthetic fibers, right? And these are all like small fibers, okay? 40 or 50 mm length and 0.4 millimeter or so. And these are steel fibers, hooked and steel fibers readily available, okay? And we try to add them and test it like this, different configurations to see. And then we put all these cameras to see the crack and so on. And then we wanted to see how they are effective, what kind of fiber dosage is effective in improving the performance, right? So we looked at, see balanced reinforcement ratio of 0.28 provided, and provided was 0.38. So it is over-reinforced. Theoretical calculation is showing that balanced reinforcement itself is very low for this section, okay? So, and this is the thing. So two beams that we have tested. This is control beam without any fiber. This is again moment curvature, and everything fails suddenly. And this is with synthetic fiber, 0.5% volume. This is with 1%. And this is with steel. Okay, steel you see, you get this is actually steel reinforced. This is a typical steel section. Okay, that's why what is it you see here? You see a lot of ductility. Steel is giving you ductility. Now this is with hybrid fiber. What is A and B? There are two specimens that we have tested. Now this is your load deflection response. So our idea was, blue color is your control. This yellow color is your steel. Somehow in the elastic regime, I want to push this curve blue into close to that of steel. That's the idea. Then I get the same performance for the same cross section, right? So that's the idea. Ultimate strength anyway for this, it will be higher, right? No problem, right? So somehow I want to do that. So you see what is that we have done? When you did HB or PO, what is that happened? Ultimate strength for steel is only 25 or so, but GFRP itself is having 35. And when I add fibers, the 32 or so, it has become even higher moment, kilonewton meter, right? So it is higher. Now higher the more the stiffer the fiber inclusion. Now which is stiffer between HB and PO in the elastic regime? If you look at the elastic regime, zoomed view, it is basically the blue one, right? So HB is having, what is that? Steel plus synthetic. Now I told you steel fibers are quite effective in arresting the crack. So I get both, right? So if I do that, the blue color curve, of a dark blue color curve, it goes very close to that of steel. Okay, that's the whole idea, right? So the serviceability performance now will become comparable. Okay, even if I put same rebar, 10 mm bar in steel, I get 10 mm bar in GFRP. But in addition to that, I also need to put some discrete fibers. Again, the cost is going to go up. Now, what is the cost of the GFRP rebar? You know, typically you guys produce maybe 150 rupees per kg.
Yes.
Roughly about 1. Steel, what is the cost? Let's say 65, 70 rupees per kg. So we can say that 2.5 times costlier, right? I mean, as of now, right? As prevalent market rates. Maybe if you look at in the US or, you know, some other country, it may be higher, okay? But what I understand is you are able to produce bars at a cost of about 2 to 2.5 times that of steel, okay? Right? So, but the density of this material is what?
Much lesser.
Much lesser. How much less it is?
4 times.
Roughly about 4 times lesser. So for same kg, I get 4 times the area of the bar that what I get for steel, right? So if the cost is doubled, you said two times, right?
Yes, it is.
So even if I double the GFRP rebar, the cost will still work out to be same.
Yes.
You understand the point, right? Because my density of the material is less. So that's what we are looking at. But we don't want to go to that level. Rather, if I put discrete fibers, what is it helping me? Multiple ways it is helping me again. It is helping me in making the failure to more ductile, and it is also going to help me in serviceability. It is also going to help me in fire resistance. So in multiple ways it is going to help. So instead of doubling the amount of GFRP rebar, why not I put my discrete fiber, I get the performance what I want. So that's the idea. Ultimate strength also is increased. That's an extra benefit that I'm getting, right? So that's the idea. Okay. Now, again, GFRP rebar, again, we have to test some bond also. Okay. Typically, the bond, because of the surface preparation, it's very smooth compared to that of deformed rebar with your rig. So, the bond is less for GFRP rebar compared to that of steel. So, we have to, how less is less? And we have to include that in our, you know, the models as well, right? So we did a lot of this bond slip testing, and then we got shear stress versus slip response for different fibers. So these are the things. This is the tension force versus slip, and then we approximated in kind of a some multilinear relationship so that we can put it into my analytical model. At the end of the day, I cannot keep testing beams, right? I have to give some guidelines for the engineers in a simplified way so that they don't need to do a lot of testing. Using the design guideline, they can do the calculation. That's the whole idea, right? So we did, okay, for different types of fibers, how the stress versus slip is, right? So then we approximated this, and then we come up with some recommendations. Okay. Okay, so you see here, this is the setup, right? You see here, this is the bonded length, 10 times the diameter, here and here. When I push it, what will happen is, you will have compression, right? So there is going to be bending moment here, right? So the bending moment, the compression will be developed in this hinge that we put it in here, and the equivalent tension will be developed, right, on the bar. Because instead of doing the simple, this bond test, this is more closer to flexural behavior. Because now I'm testing it in pure bending. The same shear stress slip, instead of doing it in this kind of pullout never happens in a realistic situation, right? But this is more closer to reality. That is the reason we do it like this.
What standard, sir?
I don't know the name of the standard. Maybe Debo can give you. I mean, we followed some European standard. I don't know the number, but I can give you that.
Put the screen number.
Yes, we did. So we did put some strain gauge. We have also put some LVDT to measure the slip. You see here, this is encased in a tube. Here, these are all tube, and it is bonded only in this middle region, so that I can measure the slip as well, right? So I can also control this diameter. What is the embedment length? to get an idea how the shear stress slip is, right? So we get this, right?
This is only due to this slab only.
Yes, yes, yeah. Bond strength is developed. So I can vary this also, if I want it. But typically, I cannot have a very long beam. So it gives you an idea how good the bond is, right? So it's a representative sample.
I have one question. What is the difference between I effective and I cracked?
What is it?
I effective and I cracked.
Okay, so maybe I should. Okay, so I cracked and I effective, right? So basically, you see here, or maybe I can go back. Okay, so you see here, I take a cross section, right? Right? What would be the moment of inertia for this section? IG is which one? Right? This is I gross, right? The same section let's say some steel is there and I apply some load and my neutral axis is here. Now what would be the moment of inertia? Let's say that at service load it is really cracked. I told service loads are going to be 65% is ultimate. Typically cracking moment will be only like what we have seen, 10 to 20% of our ultimate. So definitely under service loads concrete beams will be cracked. But we design it to make sure that the crack widths are less, right? So this is your cracked section. So what I do is, okay, let's say this is X and this is B. So I take moment of, and then I convert this, let's say this is AST. This can be converted into AM into AST for an equivalent area and then get my moment of inertia, let's say, which is I cracked. And I cracked is typically about, I said 15 to, I'm just giving, of course it numbers 20% of your IG, okay? Now, this is the least value after it is really cracked and, at highest service moment, but I don't know the moment. Let's say my moment is only 30% of your ultimate. So my moment of inertia has to be between this and this. This is the lower regime. This is higher. Okay. Oh, sorry, I think I'm not able to write it here. Okay. So I effective will be. Now what is that I effective should be? I gross, right? Now this I effective should be function of moment at which you are doing the calculations. So if my moment is very close to the cracked moment, it will be very, I effective will be close to that of IG. If it is much higher than your cracking moment, it will be getting close to that of cracked moment of inertia, right? So that's what it is. Okay, you have to do the calculation. So, so I effective is function of the moment at which that you are doing the calculations, right? Okay, you got the point?
I have one doubt, sir. Because when we calculate the I crack, we use the tensile strength of the concrete. Then at the percentage.
No, I cracked, we don't do that. Huh? So, MCR, when you do the calculations, just at the incipient of cracking,
Yes, okay.
just before the concrete is going to crack, you calculate the moment by using the stress. Okay?
This ICR is not corresponding to that MCR. Okay.
No, this is after, right after. Right after cracking, the neutral axis has gone up, at a higher service moments. Okay? That's what I said lower ending. IG, I cracked, and then I effective will be in between them.
Then sir, if that happens, then ICR should be more than I effective. Because it is just incipient.
No. This is at a higher levels after cracking in the post-cracking regime. So you see here now the I cracking. What I am doing it somewhere here, not exactly at ultimate, somewhere here, right? But this is the level at which I am calculating the I cracked. It is really cracked. But MCR is the moment which is causing the crack. At that time, the still concrete is contributing. That's why we calculate MCR. ICR doesn't correspond to the M cracking. It is corresponding to a moment which is much, much higher, but slightly lesser than M ultimate.
But still we need MCR for calculation.
Because I need to know how much I am away from M cracking. Let's say my service moment, right? M cracking, let's say in this example, what is the cracking moment that you have? Roughly about, let's say 10, okay, maybe let's talk in terms of kilonewton meter, right? Where is it? Yeah. Let's look at it here, right? So kilonewton meter is roughly what? Some 4 kilonewton meter or something, right? Here. Now, depending upon where I am, because these are all scales are very large, so you're not able to see the slope, okay? So that's why I'm just looking at where I can show you the comparisons. So the point what I'm trying to tell here is, I cracked is at a much higher service moment. Now, I have a slope like this, right? So basically what we are trying to do here is, let me assume this, okay? So the moment curvature, okay, what we are saying is this, and then you have, let's say, cracking, let's say it goes like this, and then goes like this, okay? Let's say for simple case, this is M cracking, and let's say this is M yield, and this is your M ultimate, right? Now what we are saying is, in this slope, if I take, this is going to be EIG, right? Now here, if I'm looking at a yield, okay, this slope, okay, right about this slope, we are saying that it is going to be EI cracked. Okay, this I am assuming it to be linear, but not exactly linear. Somewhat it is non-linear. Now, wherever I am taking this point, the slope, this is, we call that as EI effective. That is function of what moment value that I am calculating. Okay, let's say this is M1, this is M2, and so on. Now, this M1 and M2, I need to know how far I am away from M cracked, right? That is the reason in the equations I get M cracked. But M cracked is given to you. The moment you know your tensile strength, I know what is M cracked. But how much I am away from my cracking moment, higher I am away from cracking moment, I will get close to I cracked. I cracked. If I am very close to that of M cracked, I effective will be close to I gross. I mean, or less than that, I should say. Yeah. I mean, depending upon, how you look at it, okay? So, but you got the point, right?
Yes.
Yeah, good. Okay, so this is what we have. So then we also looked at, okay, columns, okay? And we tested for pure compression pipe. Finally, at the end of the day, we need to show the results, right? Whatever I can do, equations, all those things. Finally, I need to validate those models, right? So we did a lot of testing for columns in compression, for column under eccentric compression, column under, again, high eccentric compression, different levels. Even if you look at your load moment curves, depending upon where I am looking at it, we simulated it. Then we saw, okay, we looked at no fibers, 0.35, 0.7 and 1%, because we kept more than 1%, practically it will be difficult, right? So, then your cost, see, higher fiber addition will help. There are two things. One is from cost. Then second thing is from fracture point of view, if I add more fibers than beyond a certain value, it's not really going to give me the benefit. See, I put something and I should get something return, no? I keep putting more, I'm not getting something in return, why should I put more, right? So there is an optimum limit of fiber dosage. So we did a lot of material characterization, let's say 1%. This is good enough, right? So we did. So, and then this is your lateral load deflection curve for an eccentric case, okay? So we did, and then, so from all these things that what we can see here is, addition of fibers help me in increasing the capacity. You can see here 1350, 1450, 1471, 1610, right? Similarly, this for high eccentricity also same. The load at failure kept on increasing. Similarly, the moment at failure also kept on increasing. And I am able to also get more from the rebars. Right? So, and this is called deformability index. You see here again, more fibers I am able to get. I cannot really talk in terms of ductility, but the deformability of the system is much better. See, again, the GFRP rebars, people think that, oh, it's very brittle. But it is very elastic. Yield strain is 0.002. But what is the strain of failure for GFRP rebar? We said 2%, right? Even up to 2%, I bend it. Just before that, if I release it, what will happen? It will go back to its state. Its system is very elastic. So it's basically literally like a rubber band. It doesn't yield, but it keeps stretching. At one point of time, it will snap. But if I release the load before that, everything will go. So GFRP rebar is highly deformable system, but it's not ductile. Why we talk about ductility is there are a lot of energy absorption that goes into it. You know, when the steel is yielding, it is going to dissipate a lot of energy. But here we don't have that. You know, we absorb energy in a static sense, but you know, we don't really dissipate the energy per se.
Just so because we don't have the yield region.
Okay, yeah, we don't have that. Yeah, that's the problem, right? But I get deformability index here. So higher the fiber dosage, in fact, you can see these are all normalized. With hybrid fibers, even I get higher load resistance, right? The fibers are helping me, right? So all this thing. Then finally, we looked at this interaction diagram that we talked about. The red color is with control, only with GFRP rebar. I put more the fiber dosages, I am able to get higher capacities in compression, higher capacities in bending, and also in all combinations of compression and bending. Now with hybrid fibers, if you see same dosage, if you look at PO100 and HP100, you see HP100 is able to give me much more better performance than that of PO. Okay, so we said, okay, if you really want both ductility, strength, and multiple ways, don't just add plastic fibers, you also add some steel fibers. So you kind of mixing is also, you don't have problem. Fire resistance also you address it, and also ductility is also addressed. So that's the whole essence, right? And these are all some of the things with, you know, maybe I'll see. And then we looked at slender column. Again, we talked about slender column, right? So slender column also, okay, you know, but we cannot test a very large size column because height limitations are there. So we looked at all those things. Again, overall we said, the addition of fibers improves the performance of GFRP RC columns. Again, we looked at different fiber combinations and all. You can look at our research papers if you need more details. Maybe because of lack of time, I'll just have to skip. Okay, so this is steel, and this is GFRP without fibers. You see GFRP with 1%. I am able to push from here 60 or 65 to almost close to that 100. Now, why do I have two curves in each one of them? These are two samples because, you know, full scale, typically we do only one sample only. But here we just wanted to do two to ensure that we are getting consistent results. You see, elastic stiffness, post-cracking stiffness is all same. But somewhat there is a difference in your post-peak behavior. Okay, there is some differences there, but that's bound to happen because of the non-linearity in the system.
The GFRP reinforced concrete is effective with discrete fibers of the
even in a steel also, if you put discrete fibers, it will help.
And but to perform up to it to a certain level.
For that, we need to do the fracture test. But see, the advantage with that is fibers are again, you know, they are small length, right? So they are bonding to the concrete. When the crack is opening, what does it do? It's trying to bridge the crack, and it is helping. You know, if I anchor the fibers very well, it will help in better arresting the crack. It will also help me in dissipating that energy by pulling out. So somewhat the fiber also will pull out from the matrix. In that process, energy will be spent, right? So the fibers are helpful in improving the performance through multiple ways. One is by the stiffness of the fiber, it is going to help me the crack. In addition to that, it will undergo slipping process, pull out behavior. It will help me in dissipating that energy that is being put into the system. So in multiple ways, it is helping. But having said that, these fibers are only 30 mm, 40 mm, right? And it is anchored only for a small region. If my crack width becomes more, then what will happen? The fiber will completely pull out. So it's not that I put the fibers, it will be effective till ultimate. At ultimate, when you have large crack width, fiber effect will not be there. I mean, it is only delaying the crack and it is helping me, because compressive stress strain response also is getting altered, right? But having said that, it's not that I put the fiber, it will be effective. The efficiency of the fiber will come down close to ultimate. That's the point what I'm trying to say.
Because you can prescribe performance, we need the fibers for GFRP. Without fibers, GFRP might not perform like required level.
That's not the case.
It's not really the case. You have to look at it from case to case basis. I cannot make that very generic statement, but if at all I can make, if you add fibers to GFRP system, the performance is expected to be better. How much effective? That depends upon the cross section that you're dealing with, what type of concrete that you put in the system, what is the reinforcement layout that I have, number of factors.
If my purpose will be fulfilled without the addition, then why to add fibers, sir?
That is also true. But this is, we feel it's a more efficient way of doing it. Rather than putting 4 times the bar, you double the bar and put little bit of fibers also. It is going to help me in multiple ways. That's the idea. Right? So now this is ground supported slab. So, again, you have a lot of industrial structures, you have marine environment, and let's say coastal roads are there, always subjected to chloride. Now we can also make these continuous reinforced concrete pavement, CRCP pavement, right? So industrial warehouses, you see now a lot of Amazon stores are there, right? Everywhere you go to the city, even tier 2, tier 3 cities, you have stores. Now everything they are making it automated, right? We need to have very nice slabs, right? So, and it should not crack. And, industrial structures will be in a very corrosive environment. I cannot put and most important, as Professor Gangara was telling, GFRP was initially find its application where? Deck slabs, or in also the most important, the hospitals, right? Yes. When you want electromagnetic neutrality, nowadays we have so many hospitals, we don't want to have that interference, right? So these such kind of slabs we can do, but then you have to do. So these are the loads typically governed: thermal stress, flexural stress, and punching shear, and thickness of the slab is typically governed. Typically industrial flooring uses TR34, which is an industry standard. Okay, if it is less than 600 mm thick, must be reinforced. And reinforcement is going to help in increasing the localized load capacity, and it is going to help in limiting the crack width and crack propagation. So, and these are the typical distresses that you see in the ground supported slab. Extensive falling, joint. Typically, why do we provide joints in the pavements or floors? To release the stress, thermal stresses, right? You see that the different joints are there. I don't have time to get into all those things, so and pop-out failure, drying shrinkage, all those things. So if you want to limit the cracks, then you need to put some reinforcement. Reinforcement helps me in limiting the crack. So this is a setup that I think currently one of my PhD students is working on. We looked at 2 things, okay? This is I think 1.5 meter by 1.5 meter slab. And you see this is a load tree. We are kind of putting it under UDL, okay? So this is very, very critical. So we looked at all these things, and then this is with again steel, 0.5%, and GFRP rebar. And this is the failure mode. You see nice distributed crack. Everything is, both of them failed in a similar way. But what we find here is this fellow failed at about 500 kilonewton, and this fellow was able to take higher load.
What's the floor that is, sir?
This is a 150 mm thick slab. Reinforcement, the black is with steel and G is with GFRP.
Sir, in that diagram,
these are all cracks.
What is the reinforcement?
Reinforcement spacing that you're saying, I don't know. I mean, to be honest with you, I think what was the reinforcement? 150 mm center to center. So maybe 10 mm bar we used, 12 mm bar at 150 on both sides. Now, one specimen had steel, 12 mm bar at 150 center to center. Another one has GFRP rebar, equivalent 12 mm bar.
Same dia.
Same dia. That is the reason. See, if I increase the rebar, that's the scene, you see here, right? After cracking, it is all same. The moment it cracks, the stiffness is lost. And as expected, GFRP is having less stiffness. We know that if I replace it with same rebar. But having said that, this load is, it's about 1.5 meter by 1.5 meter, right? So even if you divide this 500 by 1.5 by 1.5, how much load it can take kilonewton per meter square? 500 by 1.5 is how much? 3 by 2.
Three times.
I mean, that's what I'm saying. It's about 300 kilonewton. So 300 kilonewton per meter square of load it is able to take. That's what I'm trying to say.
Saying that the failure is also at high.
Yeah, that's it. The FRP rebars are more deformable, right? And so this failed because it is able to see the overall energy absorption nearly remains same. Energy absorption is the area under this load displacement curve, right? If you equate that, both of them had nearly same area, but this had a better stiffness. That means crack widths are going to be less for a particular load. But having said that, the design loads are never going to be more than 10-20 kilonewton per meter square. So, but of course, this slab is for a elevated slab. Okay, and this is the worst condition that you can assume. This can be used for deck slab also.
Yes.
Now then we said, okay, how about this slab is going to perform for a slab on ground? Now what is here at the bottom?
Foam.
Is the foam. Why did we put the foam?
To test the punching effect.
Not the punching effect. Typically the slab on the industrial flooring will be supported on what? Soil, right? I compact the soil to certain density of CBR ratio, right? So we said if it is on a loose soil of a particular stiffness, then we took, instead of putting the soil and testing it, we said, okay, equivalent stiffness that we'll get it from a foam, and then we put certain thickness, and then we pushed on it. Okay, this is the two actuators we put, and we kept pushing. This is like a punching shear test. Now, what is the stiffness of this foam? I have to test it again as per the standard, and then we did this material testing to see what should be the, just like in soil, when you model soil spring stiffness you give, right? The equivalent stiffness, what should be that for the foam? This corresponds to basically a loose soil. If I increase the stiffness of the foam, obviously the soil characteristics will change, right? So then again, we did some testing, and still the work is ongoing. So again, the same idea. GFRP rebar. Again, I put little bit of fibers. Can I push it to the same level of steel? That's the whole goal. But this itself, it is giving a lot of confidence that even if you put nominal GFRP rebar for this, it is giving me a lot of performance, good performance, that what I want, right? So again, we looked at columns under cyclic loading. This is what I said. This will have the distribution of moment like this, and then this is your setup. I have a column, I put axial load, and then I push this actuator left and right. I think Dr. Jisha is also involved. They're both doing this as part of his PhD. And you see this kind of failure mode we get. Columns where, this is for steel column, right? And this is for a GFRP column. So what do you observe? Plastic hinge region in a steel is localized. Because the steel is yielding, my damage is located only in a very small region in a column. However, in case of a GFRP column, you see here, though it is not yielding, my distribution of the damage is getting longer. But again, we have done only limited tests. Now we have to test another 10 or 12 more columns to clearly say what is happening. Okay.
What might be the exact reason?
Because it's not yielding, right? It is also going to fail at a larger strain, right?
Yes.
The steel, moment it starts yielding, what happens to the stiffness of the steel? In your elastic stress strain curve, the moment steel yields, your elastic modulus 200 will become much lesser, maybe 10 or 20 like that, right? So it becomes softer, right? But in GFRP, it is not like that. It keep on going, so it is able to distribute the damage for a higher region, right? Yeah, that's what. But we cannot really clearly say that as a plastic hinge because it's not yielding. So, but the damage region is getting more distributed, we can say. Right, so this is again the load displacement curves. Again, we have to compare. This is only a trial test that we did. Now I think he will start probably.
Steel balance reduces the displacement will also increase. But since even after the cracking, the stiffness is there, so displacement will be lesser.
Correct.
So,
it's much more stiffer.
yes, sir.
Yeah, that's exactly what it is. Much more stiffer. But what is important to do here is this, you see, from seismic point of view, what is more important? It's not only strength, stiffness, it is also the area under this curve, which is called the hysteresis energy. Now, you see here, this GFRP also, it's not too bad, right? So, we have not calculated the energy and I'm not showing it, but it's not too bad. Typically, what will happen is if it is a shear dominant behavior, you will get something called pinching behavior. The energy dissipation is going to be less. okay, which is not the case that is here, right? So you get comparable performance, okay? So now anyway, a lot of work is ongoing still. Maybe next year we'll be able to give you more results on that. Yes.
What is the residual strain in GFRP as compared to steel? Like once we unload or...
Well, it again depends upon what is the level at which you're unloading, right? So either I'm talking at this cycle, this cycle, this cycle.
the elastic range, sir.
Within the elastic range, it recovers everything.
GFRP.
Yes, it recovers everything. Yeah, it is pretty much straight. That's another advantage of GFRP system. If we keep cycling it, there will not be any residual deformation. It can come back. But once it reaches its failure, then it is a different thing, right?
By seeing the graph, how do you, by seeing the curve, strain curve, how do you...
Not the stress strain curve. This is a load displacement
No,
curve.
sir, not this. By seeing the stress strain curve of GFRP, how will we decide what is the post-elastic region and what is pre-elastic region? What's the elastic limit exactly?
For GFRP rebar, everything is under elastic limit only, no? So there is no post-elastic limit per se. That you have to now look at it at the section level. See, this is a member level behavior.
Yes, sir.
What you are saying is a material level response. Now I put GFRP rebar, concrete. At the section, they act together. Now when I want member response, I have to integrate all the section response and get. So it's a little complex. So we cannot really say. But in general, we can say the energy dissipation in a GFRP system is lesser, somewhat lesser than that of steel. Now our goal again is when I add fibers, what will happen? The energy dissipation is going to get close to that of what I'm getting for steel. It may be better also. We don't know. That's what we are working on. Okay, we don't know. Okay, so these are all testing. I think Professor Gangarao already spoke about it. Maybe I'll not. One thing that I will, I want to really spend some time is this. This is the most important thing. So moisture absorption. So I think the tendency of our manufacturers is to make it more cost effective, competitive. Then they tend to add a lot of fillers. So we have tested some bars and they are not really meeting this moisture absorption. Okay. So please, my request is please don't add it. Otherwise the technology will be compromised. Okay. So cost is of course, it's very important, but you should have less than 0.25% at 24 hours at 50 degrees centigrade. But some of the result, what we are getting is, we are getting more than 0.5%. Some of the bars, I'm not saying all of them, most of them are meeting the norms. So that means the moment it is absorbing moisture, your long-term performance will be compromised. Okay, that we need to be very careful.
It will be equivalent to corrosion.
Yeah, exactly. It is equivalent to corrosion. So we need to be very careful. This technology is very good. So we have to also make sure that it is cured well, and how to test all those things that I think we have done. And then you have to meet all these norms, right? So that's the most important thing, right? Again, mean moisture absorption to saturation should be less than 1%, right? This is the limit. Or this is for qualification, product qualification. This is for quality control and certification, right? And alkali resistance also, that also we have done. After 60 degrees centigrade immersion for 90 days in an alkaline environment, as per the standard, if I test a rebar, it should have at least more than 80% of what I get for control specimen. But some of the bars we are getting only about 60, 65. Right? So it's falling limits. Short term will not have problem, but now that we are talking about 50 years service life, we don't know what the performance would be, right? So we have to be.
This contains even Indian standard also.
This is all, this exactly same values only we have kept for, I think this is, I don't know where I've taken it from, to be honest. Okay, this is the standard, Indian standard. IS 182555256. Okay, one is for how to test it. Another one is what should be the specification of the fiber, resin, all those things. Okay, yes. And these values are all taken from these standards only. It's not any different. In fact, I would say when we were discussing, we made it more stringent because we know that people try to make it more cost effective, and then there will be. But the point is, whenever we get some samples for testing, they will meet the norms. But then you need to make sure that continuously you meet that standard, right? That's the key. Okay.
There, sir, in Indian standard, there is.
Oh, here is this IS 256. This is what it is. Exactly same.
Yeah, I'm carrying that here. There are strict specifications about the additive fillers that issue too in this.
It is there.
Yes, sir.
But if you don't follow that, I am saying that you will not be able to meet this moisture absorption limit, short term and long term. That's what I'm saying. If you put a lot of fillers, this will not be satisfied.
Yes.
Similarly, you will not be able to satisfy that residual strength after 90 days of immersion in alkaline solution at 80. We have tested a lot of things and we are getting about 60% strength. Control, you get all the properties. But when I do it alkaline test, it's not meeting the norm. Some of the bars, not all of them, some of them. So we need to be careful. We should not add a lot of fillers. That's what I'm trying to say. Okay, and these are the properties for fibers and so on. Maybe I think this is what I think Debo has done some testing on compression test. Again, we wanted to see what is the effect of this. How do we characterize these bars? When I put it in columns, right? Depending upon the stirrup spacing, the slenderness ratio of this bars is going to be different, right? So what is the effect that we did? And you can see the fibers, the way it is failing, right? So, and this is the way samples are prepared, and you have to really prepare it carefully. And this is after tension test, right? And you get this kind of a broom type of failure. And this is the stress strain response in tension, and this is for steel. And tension we get very, nice, consistent results. 800, 900 we get, right? And compression we get only about, as we said, 40 to 50%. That also function of a L by D ratio. This compression test, you see here, L by D ratio 10. So you're reaching only about 300 megapascal. Why? Because it is having higher L by D ratio. So it's failing in combinations of bending and compression, right? So average elastic modulus, we are able to get about 45. There is a reduction compared to tension, and rupture strength is also lesser. Of course, it is function of a L by D ratio. Because if you want to test pure compression, you have to arrest that buckling bone, right? So we have done that. Okay, this is a compression test for 2.5. So you get this here, you get about 65. Here also, rupture strength is only about 350 megapascal. Compared to 800. So roughly we get about 40% of what you get for tension, right? So you have to look at all this. So anyways, just to conclude, GFRP bars can be used for many structural applications. And again, we feel that addition of these macro fibers increase the response of RC structures. And discrete fiber also helps pseudo ductility of concrete structure when it is reinforced with GFRP. It will not have ductility, but it will increase the pseudo ductility. That's the reason we say pseudo ductility. It's not exactly ductile. Ductility is always associated with yielding. But here we don't have yielding, but it helps in energy absorption, right? So I just wanted to give some flavor of work that what we have done. Of course, these are all so many papers and these are so many students who worked on it. Anyway, thank you. So if you have any questions, then in the afternoon, what is that we are planning? Some testing, right?
Yes.
JP? Yeah. We will go and test, yes.
Can you cover on some seasoning aspects?
Let me see. I have material for steel, but GFRP relevant I have to prepare, Maybe let me see if I can do something on tomorrow.
One thing I wanted to ask you.
Yeah.
If this bar is confined in the concrete, then its buckling is also restricted, or should we, because their bars are tested in compression.
Yeah. So this is basically after the concrete cover has spalled, right? What is the influence of this residual bar? At higher strains, when the stirrups are kept at a longer distance, what is the significance of this, right? So that's what it is.
If the slenderness is very good, still the bar will just bend and
The bar will?
the failure mode will be not buckling or just...
Oh no, the stirrup also is there, right? Now the stirrup, again, the behavior of the bar after concrete cover spalling is also a function of what is the effective length. That's what is the effective length. We consider two different effective length, right? When it is 2.5 means the stirrups are placed very closely. When it is at 10 means the stirrups are placed at a larger distance. So this is the worst case scenario.
Sir, I'm not able to visualize how it will compress because what I have seen that the fibers bend and then crack. Not like actually it doesn't bulge.
See, again, it's like a slender column, right? If I put axial compression, because of its virtue of its deformation, again P delta effect will come, right? Higher the length of the column, longer the length, higher will be the susceptibility to elastic buckling, right? So that's what we are saying. So it is going to fail. See, as it is, the fibers are not very effective in compression because the resin has to be keeping them in intact. Otherwise the rope, you see, it cannot take compression, right? Basically, fibers are like rope, but you have kept everything and you made it hardened with resin. And then it is effective in transferring compression up to a certain limit. The moment micro cracks develop and then that bond is lost, then the efficiency of transferring load is going to be less.
Yes.
That's why in compression, that is the reason the ACA code not allowing you to take contribution of bars in compression.
Yes.
Because for design purposes, we have to be conservative, right? For research, we include all those things to understand clearly what is the role, right?
One more question. So, like a member is designed in steel, as steel reinforced member. When you want to design it for FRP, how we convert those, how can I say this? Like a percentage or rebar percentage or the reinforcement.
Well, that's what I'm saying. We cannot tell quickly that you replace this bar with this. You have to check the failure mode and what is the performance. I need to first be clear about what the performance requirement, right? Let's say I do a beam. I have to make sure that the deflection cannot be more than 20 mm. And at this particular service loads, this should be my crack width. Then you back calculate. So first you have to be very careful about what is the performance requirement you want.
Yes, sir.
In terms of strength, in terms of ductility, in terms of serviceability. Then you back calculate what is the you want.
Also, there are stringent requirements because 1.4 row times have balanced reinforcement ratio we take for the FRP bar.
Yeah.
Reinforcement. So if you back calculate, then it will be overstrengthened and means if you back calculate.
Yeah, that's true. That's exactly what I'm saying. So design is always an iterative process, right? So you do some preliminary design and then you optimize your design based on all these conditions, right? The guidelines gives you how to start and go about it. The more you design, then you know exactly what parameters to look at it.
Like if we try to fulfill the strength requirements as per the steel reinforcement, then we will not be able to fulfill the specification.
Yes.
Design as per the service, then maybe we will
Over design.
Yes,
And you need to iteratively do it. You do 2 projects, then the 3rd project you know exactly what you need to do. That is what your experience that you have to develop.
or should we, for the research purpose, we should not consider that 1.4% row FB and
See, these are all guidelines are coming up with whatever our experience so far in the last 20 years of using this material, 25 years of using this material. That's why we are doing this research. More and more you get data, more and more confident you are getting. Again, the problem is what? We have to be conservative. The bar coming from one manufacturer is not equivalent to the bar coming from another manufacturer, no. So then I have to take the lower bound so that people don't abuse the technology. So let me put it this way, right? I think it's not straightforward. I cannot always say draw parallel. You have to do a lot of trial and error and then come up.
I also think one thing, sir, you have said put the same reinforcement ratio for steel and FRP.
Correct. Our idea was to compare,
Yes, sir.
So that what is the performance, because I'm also adding fibers.
Yes, sir.
So then I don't want to overdo it, right?
Yes, sir.
And one more testing that we wanted to do is for equivalent system. So equivalent will be the stiffness, the E into A for steel and GFRP, we want to make it same. Then I'll put 4 times. That results we have not shown, but in some of the papers we have done it in the calculations. So we have not shown, I have not shown here.
You have increased the reinforcement.
Correct. That also we have seen. That it gives much better performance than that of steel.
Yes, sir.
But I don't need that. Then I put a lot of material.
But it might not be economical also.
Uneconomic. So it will be highly uneconomic.
Yes.
That's the point.
And sir, one more thing, Gandharv sir told us that energy dissipation in case of reinforced member is higher than the steel reinforced member.
Energy absorption maybe. Again, it depends upon what kind of loading that you're looking at. Like I told you, again, this system is also having energy absorption. But for me, I want warning before failure, static loads, right? But this system does not give me as much as warning as we get from steel. Because the moment it's steel, you have a lot of cracking, the beam will deflect so much, something is wrong.
Something is absorbed, but it is not
Dissipating.
Yeah. Well, dissipation is in cyclic load. Energy absorption is good, but again, what I'm saying is you may not see much cracks, but it will deform. But in steel, when you see a lot of cracks and deflections, you know that the steel is yielding, something is wrong. But with GFRP, even though deflections may be less, if you put a lot of GFRP rebar, and then suddenly it will give up. So it does not give you that warning as much as the steel gives. That's the problem.
So dissipation and absorption, what is the difference? Like absorption is
See, absorption is under static load. The area under the load displacement or your stress strain curve, whatever the area that is there, is the energy absorbed by the system. When you say dissipation is, there is an input energy that is coming from an earthquake that has to be some way, it has to be dissipated. Either you put a damper or the material should degrade in the form of cracking, yielding. That's what we say from cyclic loading point of view. The area under that curve is the energy dissipation. Hysteresis energy.
the area.
Material.
Area under curve is also absorption and area under curve is also dissipation. Or there is
So that area of the
It's just a nomenclature. Typically, what we are saying is from cyclic loading point of view, the energy is being put and it is dissipating because you have cyclic loading, right? So that's what it is, right? It's basically the energy. I mean, from seismic point of view, from cyclic load point of view, we say that the energy is getting dissipated. But from static load point of view, it is being absorbed by the system. So that's all. But at the end of the day, it is energy. Yeah.
Have you tested any guides also that we involve?
No, we have not. I think we were planning to do, but again, we have to go step by step. If you give me a lot of money, then we'll test. But the problem is getting research funding is an issue. Yeah. Yeah. Good.
So,
Maybe I think we're almost time. Maybe we'll talk during the lunch. Yeah. Go ahead.
it would be short, sir.
Yeah.
Which thermoplastic resin did the company use, the manufacturer? Do you have-
I don't know. To be honest with you, I don't know.
Was that manufactured from Hyderabad or from somewhere?
It is from Hyderabad. I'll get you the details. I don't know. To be honest with you.
Okay.
I don't know. I'll get you the details. Yeah, yeah. But the process is exactly same.
The process
You have to optimize.
is just,
Yeah.
I mean, if you're using a thermoplastic resin, the percentage of additives also,
Correct.
it changes a lot.
Yes, absolutely. I don't know the details, but concept is this. Basically to bend the bars in the side so that you can make stirrups and put it in the system, right? Yeah. Yeah. All right. So we'll take a lunch, and then we'll meet in the lab probably at 2:30. It's 1:30 now. Yeah. All right. Thank you, everyone.